Can you write the recursion for me? So what is T and M
T
in
of
terms of
MM
subproblems?
is equal to whatever the time it 2t, the time it takes to solve 2 problems of half the size plus like what we just discussed O of M, because that's a combined.
O of M plus N, because the divide is O of N as well.
Oh, because we have to count the divide.
Yeah.
Oh, fine. We need to fix this eraser by the way.
Yes, exactly. And so, okay, so now if we want to...
Yep.
Yes, exactly. Exactly, yes, that is exactly correct. So now if we want to analyze the runtime for this here, then what can we notice here? Okay, so let's just do a recursion tree, just to see what is the runtime. So first of all, you can see that this is a correct algorithm, right? This is a divide and conquer algorithm that actually evaluates our polynomial, right? Are you convinced that is the correct algorithm?
Yep.
So it's correct. So it does the transformation from the coefficient into the evaluation, right?
Yep.
So we just have to analyze its runtime. So let's draw a recursion tree. At the first level, we're going to be having the degree is n, and the number of points is n. Then we're going to be recursing on 2 subproblems. These subproblems, this is going to be having a degree of n over 2, but as we said, the number of points is not going to be changed. So this is going to be n. This is n over 2, n. Then this is going to be dividing into 2 subproblems. This will be n over 4, n, because n will not change. We will evaluate it at the same number of points. And here, we will have n over 4, n, and the same thing here. Okay?
Yep.
You're with me, okay?
Yes.
Okay, so now if we look at how many work is being done. So here, because we now use this part here, 2n work is being done, right? Because it's n plus n, right? Here we have n plus 2 plus n, that's 3n over 2, right?
3n over 2.
And here 3n over 2. So that's how much?
Well, I don't get where the 3 came from.
So like we know that at every sub problem we are spending a cost of m plus n, right?
Yep.
So here we have, this is our n and this is our m, right?
Yep.
So here we have an order n work, right?
Yeah.
So now if we want to think about how much work is being done on this level, then we know that...
Oh, right.
Yeah.
It's n, right? Wait. Oh, it is. Well, it's weird. It's 1.5. Yeah, it's 3n. It is 3n. It's 1.5 each, isn't it?
Yes. So it will be 3n.
Yeah.
And then here we will have...
1.25 times 4, which is 5n.
Okay, yes, but to make things simpler for us, let's just because we're making a lower bound here. By just counting the n's here, we see that we have n here all over the place, and the n is every time we're branching out, right?
Yeah.
So if we think that as we're branching this tree out, how many leaves are we going to be having here? If we have
we're gonna have 2 to the n.
2 to the n. Think about it again. What's the height of the tree?
Oh.
Just think.
So at the start is 1. So 2 to the 0.
No, wait, what is the height of the tree?
Height of the tree log n.
Exactly. So log n. So now, is it 2 to the n or 2 to the what?
How you're talking about how many n nodes?
How many leaves?
Leaves,
at
yeah.
The bottom.
How many leaves? I think it is somewhere around 2 to the n. Yeah.
So if we have
Oh,
a
2 to
height
the
of
log n.
exactly 2
Sorry.
to the log n.
My bad.
So 2 to the log n. So we have n leaves, right?
Yes.
And we know that every leaf has n in it because we know that this n here, the second n, does not change. Right?
Yep.
So we know that we have order n squared work just at the leaves, right?
Yes.
So we haven't improved. This does not improve anything, right? So we are still taking order n squared to evaluate this polynomial by just analyzing this recursion tree.
Yeah, I
right?
guess. Yep.
Yes. So even though we haven't improved, actually we're very close because there's one crucial problem that is making us slow. And the crucial problem here is that this n is not growing smaller. I mean, it's not getting smaller. It's always being fixed. We are always evaluating at the same number of points, no matter how small our degree is. Like even if we divide our degree by 2 every time,
Yeah.
we're keeping the n the same. So it seems that we're doing a lot of overwork. We're doing a lot of
that is
redundant
the.
work. Because for example, like if you have a polynomial of degree 3, you don't need to evaluate it at 50 points.
Yeah,
And
that is
eventually
true.
that's what we're doing because we are, for example, starting with a degree 100 polynomial. So we're evaluating at 100 points. And then 100 becomes 50, and then 50 becomes 25, and then 25 becomes 12, and then 12 becomes 6, and then so we have a polynomial of order 6 that is being evaluated at 100 points, which is a lot of work. So if we are able to make this n actually, instead of staying n here, to actually go to n over 2, so if we actually somehow make this m divide, so instead of m here, make this m over 2 here, then what will our recursion become? What do you think our recursion will become?
Well, at the second step, it would be n over 2 and n over 2. So it'll be n. It'll just be 2n. It'll always be 2n. Wait, it wouldn't be.
So let's first think about it even at an earlier stage. How many parameters now do we have to our subproblem? If we know that every time we divide our degree,
There's just one
also,
parameter.
Exactly. So it's only one parameter. We'll call it n. And n here will represent the degree and will also represent the number of points because at this point they're going to be the same. Because we know that at every time we are dividing our degree, we're also dividing the number of points we're evaluating at, right? Do you get this?
Yeah, of course.
Okay, so now if we want to convert this, if we want just to convert this to this, it will become simply 2t of n over 2 plus O of n, right?
Yeah.
And by the master theorem, this leads us to order n log n. Right? Do you remember the master theorem?
Yeah.
So I can also analyze it to you using a recursion tree if you want to understand it even more. But
this is
by the
master
master
theorem. Wait. N log b of a. This is. It seems like every. Yeah, that makes sense, right? So there are log n levels. This is a number of levels, and then it's constant work.
Exactly.
Now wait. 2t of n over 2 plus O of n. Is O of n because to combine takes n over 2, and then to divide takes.
No, here to combine takes order n, and to divide takes order n.
I see. So it's kind of like O of n plus n is still O of n.
Exactly. Right. That is exactly true.
Okay, cool.
Okay?
Yeah, all good.
So now you are convinced that if we can somehow divide the number of points at each iteration or at each recursion, then we have basically solved our problem. And now we have an O of n log n algorithm.
Yep.
Okay,
Now how do we
so
do it?
this is the final step. This is the final thing that we need to do. We just have to figure out a way to make the number of points divide in 2 at every time we recurse. Okay?
Yep.
So I'm gonna save the doodle now. Again. Wait, you save it. You save it.
I save? Okay. FFT part 5. Save. It's saved.